So in this video, I want to make sure that you understand the relationship between wavelength and frequency and get some of the mathematical relationships down and maybe even practice a few of those problems. Now, here we have the electromagnetic spectrum, but it's shown just a little bit different, okay? And so you can see the parts of the electromagnetic spectrum. Here is, the visible light, UV rays, gamma rays, X-rays, all of those things that we saw in previous videos, okay? And so what we should look at is that, and what we should already know is that as wavelength gets smaller, frequency gets bigger. Okay, as the wavelengths get closer and closer together, that means more of them can pass a point in a certain amount of time. And so what that means, and that's kind of the interesting thing, is that the low energy waves are on this side of the electromagnetic spectrum, and the high energy waves are on this side of the electromagnetic spectrum. If we really think about it, we are being bombarded with TV and FM radio waves and cell phone signals, all those things that are down here. Okay, those never hurt us. They do not have a lot of energy. Okay, visible light sure as heck doesn't have a lot of energy. Okay, but once we start getting into like the UV rays, okay, UV rays can burn us, right? That's what sunburn is. X-rays are so strong that they pass right through us, and gamma rays, thank goodness for the Earth's atmosphere, but gamma rays can cause severe problems almost instantaneously. One of the biggest problems when people go into space is to try to figure out ways to shield astronauts from gamma rays. It's a big thing. So the low energy here is because it has a small frequency and a long wavelength. Okay, and so here's another representation of that same thing with some numbers plugged in here. Okay, and so if you want, you can pause and take a look at that. Okay, that's the Greek letter for gamma, if you didn't know. Okay. Now you'll notice that on some of these slides, you'll see things like nanometers. Okay, well, unfortunately, you're going to have to be okay with converting, and you're going to have to understand that the unit of wavelength we usually measure in meters. Okay, but when we see gamma rays, we usually measure them in picometers, and when we see visible light, typically we'll measure it in nanometers. But if we're going to do any math with them, you have to make sure that you can convert to meters. Okay, and so this just kind of gives you the idea of the conversions and what you need to do. Okay, now how is it that wavelengths, long wavelengths, have low energy? Okay, I hope that having a long wavelength kind of makes sense in terms of having a low frequency, but let's think really about why it has a low energy. Okay, let's say we have a photon. Now, I haven't talked about a photon yet, okay, but a photon is kind of an important concept here. A photon is a particle of light. Okay, it's a particle of light. And that particle of light is the characteristic of light that we are trying to measure. Now, the photon is kind of interesting because you can consider it a particle, but it also travels in waves. So, so what ends up happening is that light can be considered both a wave, which we've been talking about all this time, but it also can be considered a particle. So there's something called the wave-particle duality, where light can act as both. Maybe more on that later, but for now, just realize that light is made up of waves. The easiest way that I have found to think about it is imagine that there's a photon, and instead of that photon traveling like in a straight line, like kind of a baseball, okay, imagine that photon is traveling in a wave, okay. That would be kind of the wave-particle duality in a simplistic sense, okay? But look at what happens, okay, as that thing travels. Notice what happened to the green one versus the red one, okay? Let's see if I can back it up. Let me get rid of some of this stuff here so that it's not doing that. And I'm breaking the cardinal rule of screencasting as I'm rewinding it and redoing it myself, but it's fine. Notice that green dot, okay? It's going crazy down there, okay? It's going crazy down there because it has to travel many more times to get all the way down the path, okay? Okay. And that means it needs a lot more energy. So look, the red, if you were to fill that whole thing, because it's a continuous bunch of photons traveling in that wave, okay, and then you do the same thing with the green, look, the red and the green, the red has 60 photons, and the green's going to have 162 photons. Which one's going to have more energy? Well, the one with more photons. And that's kind of why there's more energy in shorter wavelengths. Okay, so now we've come up with this relationship. Okay, I'm going to try to move on here. Low energy, high energy. Okay, and so I'm going to skip over the red and blue light. Okay, photons traveling, right? Particle of light, photons, there's the thing, and we'll talk about what a quantum is, okay, and this is the wave-particle duality. Light photons travel along in this wave, and that's kind of neat, okay, but let's talk about the relationship here, okay, the mathematical relationship. Okay, C equals nu lambda. Keep in mind that nu, again, frequency and wavelength. Okay, c is the speed of light, and that's important. The speed of light is a constant. Okay, the speed of light is always going to be this, and I will always give you that value. Okay, and so now let's do, if this is always going to be 3 times 10 to the 8th, here's that value. Okay, if the frequency increases, what has to happen to the wavelength? It has to go down, because this has to stay the same. If one goes up, the other has to go down. And then the opposite is true, and I'll do it in a different color. If this one goes down, then that one has to go up. This is the relationship between wavelength and frequency. And if you ever want to memorize this formula, and again, I'll give you the formula whenever, I always say it's Mary's formula, because Mary had a little lamb, right? C, the nu lambda. There it is, okay? So, and this shows that relationship, okay? Now, the other relationship, which we know is energy is related to the frequency, and because it's also related to the wavelength, and so because we know that frequency and wavelength are related to up here, okay, that as the energy, or sorry, as the frequency increases, now the energy is going to increase too, because they both have to go up. Well, that's exactly right. And that's because this value right here is Planck's constant. Max Planck, if I pronounce that right, was the guy who researched all this stuff. And so they gave him this constant. It's the constant that shows how energy is related to frequency. It's always going to be 6.6 times 10 to the minus 34 joules per second. Okay? And so much like this has a constant right here, this formula, Mary's formula, it's not actually called Mary's formula, just so you know. But c equals nu lambda, c is a constant. Well, this is a constant. Okay. Now, and if you do the F convention, there it is. But now, where does this formula come from? Well, this shows how wavelength is related to, right? And so how this comes, this is a combination of this. If we set this formula equal to F, we'll get C over lambda, and then we substitute it in here. So these are the three relationships that light waves have, okay? And so this explains kind of in words what's going on. And here's Mary's formula, C equals nu lambda, right? Okay, this gives you this. Wavelength, we always need to make sure that we convert to wavelength in meters. That's important, okay? And so that's something. We may be given it in nanometers or picometers or centimeters, but we have to make sure it gets converted to meters before we do any of the math, okay? And so here's the example, okay? Find the frequency of a photon with a wavelength of 434 nanometers, okay? Well, here's what I'm going to do, okay? Let me actually stop here. I'm going to put this problem on its own video, only this problem, and that way we can go through some of this stuff. Okay, so check out the next video and we'll go from there.